Well, now that we've talked about Raoult's law, we want to look at the phenomenon of boiling point elevation and freezing point depression. The first part of this, the boiling point elevation, is directly related to the fact of vapor pressure lowering. That is, that quantity that we just calculated with Raoult's law is directly related to the fact that the vapor pressure is lower for a solution than it is for the pure solvent. As you recall, when we look at a phase diagram, this particular line represents the vapor pressure curve. It's the vapor pressure at different temperatures as we go through and increase those temperatures. Well, when we have a solute in there, that's going to cause this line to shift down because it's lowering the vapor pressure, and it lowers the vapor pressure throughout that solution. Well, because we're lowering the vapor pressure, that means that our new line, which is the vapor pressure of our solution rather than our solvent, it is going to have a higher temperature at which it crosses 1 atmosphere. If you recall, the temperature, the boiling point is equal to the temperature at which the vapor pressure equals 1 atmosphere. For the pure solvent, it was here, but for the solution, it's a little bit higher. Well, that change in temperature we call the boiling point elevation. We can calculate that using a simple formula that I'm going to show you here in a moment. Now, we've also got another phenomenon, which is that whenever you have a solution, it's going to have a lower freezing point than the pure solvent. The reason is that when a solvent freezes, it forms a crystal, but if there is something in that, something that's blocking the crystal from forming, it means you have to go to a lower temperature to get that crystal to form. And so you can have a decrease in the freezing point. Now, sometimes that freezing point depression can be very small, sometimes it can be very large. It really just depends on what your solvent is. But the formula for calculating that freezing point depression is going to be very similar to the formula for calculating the boiling point elevation. So now I want to show you what those formulas look like. All right, so here is the formula for the boiling point elevation. Delta TB is the boiling point elevation. It is equal to KB times the molality of your solution. The molality, the KB, is the molal boiling point elevation constant, and it's going to be in units of degrees Celsius per molal. Molality here is simply going to be the molality of your solute in your solution. Again, it doesn't really matter what that solute is. All that matters is what the boiling point or what the concentration of the particles is. So Kb times the molality, and then when we put that in there, that will give us delta Tb. That delta Tb we're going to add to the normal boiling point of our solvent. So once we calculate delta Tb, we want to add that to our normal boiling point. All right. Now, in a similar fashion, we can calculate the freezing point. The freezing point depression. The freezing point depression is equal to Kf times the molality. Kf is called the molal freezing point depression constant, and again, it is in degrees Celsius per molal. And then, so Kf is that. M is the molality of the solute. Once we calculate delta Tf, we're going to subtract delta Tf from the normal freezing point. Okay, so now we are calculating that. So the big difference here is this, the delta Tb we add to the normal boiling point, and the delta Tf we subtract from the normal freezing point. Let's just do part A of number 68, which is the next one on the in-class assignment. All right, so here's number 68, and again, we're going to do part A. All right, slow my cam down just a smidge. All right, so there we go. There is the molality, and we're going to calculate the boiling point elevation and the freezing point depression. So delta TB is equal to KB times the molality. So delta TB is equal to KB times the molality. We'll come back over here and we'll look at, so for our delta TB, we're going to look at the KB for water. And then the problem gives us, the molality, but the KB for water is 0.51. So I'm going to come back over here and put 0.51 degrees Celsius per molal times 0.40 molal. So 0.51 times 0.40 equals 0.204. All right. Yes, I wrote down our solvent is ethanol. I wrote down the wrong freezing point, our boiling point elevation constant. All right, let's just go back and grab that real quick. Our boiling point elevation constant for ethanol is not 0.51, it is 1.22. So 1.22 degrees Celsius per molal. So let's try that again. Okay, so 1.22 times 0.40 gives us 0.488 degrees Celsius. So 0.488 degrees Celsius. We'll need to round that to 0.49 degrees Celsius. And because this is delta TB, we want to add that to our normal freezing point, our normal boiling point, to give us our new boiling point. So our new boiling point is going to be the boiling point of ethanol, which I'm going to go back over here. You'll see the boiling point of ethanol comes out to 78.4. So 78.4 degrees Celsius plus 0.49 degrees Celsius. All right, so 0.49 plus 78.4, and that gives us 78.89. We're just going to call that 78.9 for sig fig purposes. So 78.9 degrees Celsius. All right, so next we've got delta TF. Delta TF is equal to KF times the molality. All right, so delta TF is equal to KF times the molality. Our KF for ethanol, again, this is almost the same calculation, except we're going to have a different value for that KF. So the KF for ethanol, you'll see here the KF for ethanol is 1.99 degrees Celsius per molal. It's over here. So 1.99 degrees Celsius per molal times 0.40 molal. All right, 1.99 times 0.40 equals 0.796 degrees Celsius. Since we only have two sig figs, I'm going to call that 0.80. So 0.80 degrees Celsius. All right. With delta TF, we want to subtract that from the normal freezing point of ethanol. The normal freezing point of ethanol, again, we'll go back to this table, is negative 114.6. So our normal freezing point is going to be negative 114.6 degrees Celsius minus 0.80 degrees Celsius. So negative 114.6 minus 0.8, and that gives us negative 115.4 degrees Celsius. All right, so that is our new freezing point for that. All right, before I carry on with this next one, we're going to need to do an additional calculation on this one. So here we've got decane and chloroform, and our solvent is the one that it is in, so it is in this much chloroform, so that is going to be our solvent, and our solute is the decane. Well, we'll need to figure out how many moles of decane there are, and then calculate what the molality of that decane is in this. So first, let's calculate the number of moles. So 20.0 grams of C10H22 . All right, so C10H22, and our molar mass, I calculated that for C10H22, comes out to 142.34 grams of C10H22. Oh, that's 32, not 34. Not a huge deal, but might as well get it right. So 32 C10H22 per mole of C10H22. So 20 divided by 142.32, and that gives us 0.1405 moles. Now I am going to round here in just a moment. All right, so I'm going to round that. Our molality is going to be 0.1405 moles, and we need to divide by the kilograms of our solvent. Our solvent is this. You'll see it's in grams, so we're going to write that in kilograms, and we'll get 0.0455 kilograms. All right, so 0.1405 and then 0.0455. So 0.1405 divided by 0.0455, and that gives us, we have 3 sig figs at this point, so we should go ahead and round that. We'll call it 3.09. All right, well now we're going to use that in all of our calculations to calculate KB, or delta TB and delta TF. Delta TB is equal to KB times the molality. Our molality here is 3.09, but we'll need to look up the KB for chloroform, CHCl3. So we're going to go back over here on this table, CHCl3, and our KB is 3.63 degrees Celsius per molal. So 3.63 3.63 degrees Celsius per molal times 3.09 molal. Right? So 3.63 times 3.09, and 3 sig figs there, we'll just call that 11.2. So 11.2 degrees Celsius. Since this is delta TB, we want to add that to the normal boiling point of chloroform. So we're going to go back to the list over here. We'll see our normal boiling point of chloroform is 61.2. So TB is going to be 61.2 degrees Celsius plus 11.2 degrees Celsius. All right, so 61.2 plus 11.2 gives us 72.4 degrees Celsius. All right, now we just want to do the same thing, but for delta TF. So delta TF is equal to KF times the molality. All right, KF, again, it's going to be different than the KB. So we'll go back over, look for chloroform, and KF is 4.68. So 4.68 degrees Celsius per molal. And we'll multiply by the molality of 3.09 molal. So 4.68 times 3.09, and it's 14.46. We've got 3 sig figs, so we're going to call that 14.5 degrees Celsius. Since it's delta TF, we want to subtract that from the normal freezing point. So we'll subtract that 14.5 from the normal freezing point. And so our new freezing point, come back over here, our normal freezing point for chloroform is negative 63.5. Negative 63.5 minus 14.5 degrees Celsius. And so negative 63.5 minus 14.5, and that gives us negative 78.0 degrees Celsius. And that is our new freezing point. So you can see that we can have a pretty significant impact if we put enough of the solute in there. So we can get a pretty significant impact. All right. Well, next, on this next one, something interesting is happening because we have an electrolyte. The potassium bromide is an ionic compound. And so we have to treat it a little bit differently than we would normally treat a non-ionic compound. So, let's go back. Let's go back to the presentation and look at these properties. So the point of this page is that they are colligative properties, and colligative properties depend on how many particles are present, not on the identity of those particles. However, if we have an ionic compound, then we need to pay attention to how many particles there really are, because if you take an ionic compound and dissolve it in water, those ions will dissociate. So here, for example, sodium chloride, when it dissociates, for every mole of sodium chloride that dissociates, you don't get 1 mole of particles, you get 2 moles of particles. You get 1 mole of sodium ions and 1 mole of chloride ions. Well, it turns out those ions act like individual particles. So for colligative property purposes, they are independent of each other. If we were to have a 1 molal solution of sodium chloride, we would see that it would have a significantly higher effect on the boiling point or the freezing point than a 1 molal solution of, let's say, methanol. And the reason for that is that methanol is not an ionic compound. It does not dissociate, and so it will not have a larger impact. What's kind of interesting about this is you would think, all right, if I have a 1 mol solution of sodium chloride, it should have twice the effect of a 1 mol solution of the methanol. Well, that turns out that that's not the case either. It's not quite twice the effect. Now, it's pretty close to twice the effect, so for purposes of this class, we can assume that it's twice the effect, but let me show you why it's not quite twice the effect. So whenever ions dissociate, to the extent that they are dissociated and they're apart from each other, they act like independent particles. So this sodium ion would lower the freezing point of the water separately from this chloride ion. However, if we have a sodium ion and a chloride ion that are close to each other, they will have the effect of acting as one particle. So that to the extent that you get this kind of thing happening, where you get what's called a close contact ion pair, it will decrease the effect of that electrolyte. So, so again, we call that a close contact ion pair, and it has a somewhat decreased effect on the freezing point. So that is called the Van Hoff factor, and we can get a measure of how much of this reassociation occurs. Now, it's a little bit tricky because this reassociation effect is concentration dependent, which I'll show you on this next page. So it depends on how much of the stuff is there. This is why we're not going to actually do these calculations. We're just going to assume that it completely ionizes. But you'll see at 0.001 molal, it's less than the expected value of 2. Since there are 2 ions, it's less than the expected value of 2. It's at 1.97. That's because a small percentage of the ions reassociated as a close ion contact or close contact ion pair. Here at 0.01, that effect goes down to 1.94, and at 0.1, it goes down to 1.87. So you could imagine as you go to even higher concentrations, this could be pretty significant. All right. So in place of the 2, we're going to use the 2 for our calculations, by the way, but in place of the 2, you could use the Van Hoff factor I and modify your formula in this fashion. We are just going to treat the ions as independent of each other. So let's do the last part of number 68. So we'll do the last part of number 68. And the way that I want to think about this is that the molality of the particles is going to be equal to the moles of particles divided by the kilograms of the solvent. Well, the moles of particles, all right, the moles of particles, here we've got 0.45 moles of ethylene glycol. Ethylene glycol is not ionic, so that acts as 0.45 moles of ethylene glycol plus 0.15 moles of potassium bromide. Well, that's going to act like 0.15 moles of potassium and 0.15 moles of bromide. So I'm going to put 0.15 moles of potassium and 0.15 moles of, I ran out of space there, bromide. And then we're going to divide all of that by the kilograms of solvent, where our solvent is 150 grams, so we have 0.15 kilograms. All right. So 0.45 plus 0.15 plus 0.15, and that equals 0.75. And then we divide that by 0.15 kilograms. And that gives us 5.0 molal. So the molality of our particles is 5.0 molal. Okay, so now we'll do the same calculations we did before, which is delta TB is equal to KB times the molality. And we'll do a separate calculation that's delta TF is equal to KF times the molality. So for KB, we want to look up the KB for water. And to do that, we're going to need to go back a couple of pages here. Here's our table. Our KB for water is 0.51. I accidentally tried to use that one a little bit earlier for ethanol, but 0.51 degrees Celsius per molal. And I'll go ahead and get the KF while I'm over here, 1.86. 1.86 degrees Celsius per molal. All right, so our KB is 0.51 degrees Celsius per molal, and our molality is 5.0 molal. So 5.0 times 0.51 times 5.0 times 0.51 gives us 2.55 degrees Celsius, and we're going to round that to 2.6 degrees Celsius. So 2.6 degrees Celsius. All right, so now let's add that to the normal boiling point of water. We don't need to look up the normal boiling point of water. The normal boiling point of water is 100 degrees Celsius, and we're going to add 2.6 degrees Celsius to that. And look, Ma, no calculator, 102.6 degrees Celsius. So we would have increased the boiling point by 2.6 degrees Celsius. Now, for the freezing point, it's a very similar calculation. I wrote this down when we were over on that other page a minute ago. 1.86 degrees Celsius per molal. We'll multiply that by the 5.0 molal. So 5 times 1.86, and that gives us 9.3 degrees Celsius. So we'll take that 9.3 and, of course, subtract that from the normal freezing point. Our normal freezing point for water, of course, is 0.0 degrees Celsius minus 9.3 degrees Celsius. Again, no calculator needed here, negative 9.3 degrees Celsius. So we can, by adding some ionic compounds, significantly reduce the freezing point of water. And this is exactly what we do during the winter whenever we have snow or ice. If you want to get the ice off of your sidewalk, you can just sprinkle a little bit of salt onto it, and that salt will cause the freezing point to go down. You can melt the ice, and in turn, in melting the ice, you can get it to evaporate, even if the temperature is below 0 degrees Celsius. So pretty cool. All right, so that is the boiling point elevation and freezing point depression. We will do osmotic pressure on the next video.